And this is the plan of these 3 lectures. I tried to be not extremely technical and as comprehensive as possible. We'll start with a review of the situation, with what is the status of electrovacuum black holes and black hole uniqueness and the concept of hair and the Bekenstein theorem and various mechanisms for the scalar hair. This was the plan for today. Let's see, perhaps a bit too ambitious. Then the second talk will be the class of special class of black holes with synchronized hair. Carlos mentioned already, and go beyond GR and discuss also scalarization. And finally, the plan is to approach other types of hair, vector hair, other models, and finally some overview, general picture. So I think you could stop me anytime. I'm very happy, or at the end of the talk of the presentation, I'm very happy to try to answer all possible questions and some useful message, some useful feedback. Now there is some overlap with Carlos' previous lecture. I thought it's a good idea to start with a general review. Why do you know there are black holes? Why do you know the black holes are there in the universe? And we have strong evidence coming from astrophysics. So no indication so far for microscopic black holes, although there are all kinds of theory hints in this direction. And about astrophysics, there are basically 2 directions. It's the observation of time-like and, basically null time-like and null geodesic trajectories, stars or lights. And here we have observations of orbits, in addition to what Carlos said before, well, was mentioned already, in fact, and these black hole shadows. And finally, a different channel recently, the detection of gravitational waves. And so far, black holes seems to be the best explanation we have. So there is evidence for the existence of some special type of objects, ultra compact, and among all possible explanations, black holes are the best. And here, let me mention very briefly the 2 cases, the black hole at the center of our galaxy. So I apologize, this is the previous version. Anyway, doesn't matter. Okay, so that's fine. Not so important, it's almost the same. Okay, so, yeah. It was updating briefly the slides, but that's fine. It's not. Yeah. Anyway, so there is a great time for black hole physics. Okay, that's very small differences. Let's go. We are living in the second golden age of black hole physics, people used to say. There was a fantastic decade. In 2016, it was the detection of gravitational waves. Then a Nobel Prize for that next year. Then 2019, 2022, it was the direct observation of black hole shadow. First, this one for M31, and last year for Sagittarius A at the center of our galaxy. And finally, in 2020, it was a Nobel Prize on Physics for black hole physics. So I think black holes are in this moment widely accepted by the community, which was not the case a few decades ago. It was much stronger resistance. Now they are widely accepted. Now, the black hole concept, interesting enough, is not really new. Here I put in physics, I put some historical overview. It started in 18th century with the work of John Mitchell and Laplace. And then they were called at that time dark stars. This concept was introduced based on fully on Newtonian physics, and one can understand some aspects of black hole physics without using general relativity. So this is a capture of the first page of John Mitchell's scientific paper in 18th century about the concept of black holes. It's supposing the corpuscular model of light. It's proposed by Newton. Then if there is a body which is with large enough mass, then it will be invisible for sufficiently far away observers. So a number of things are already captured there. Now, the theory of gravity in this moment is based on geometry. We have a geometric understanding of gravity, very different from Newton. We are solving partial differential equations. It was Einstein's general relativity, which gives us the framework in 1915, equating basically the curvature of space-time with some distribution of matter via Einstein equations, field equations. And then the first black hole solution was found very briefly after that, 1 year later, by Carl Schwarzschild. Here I put a capture from IOP website. It's very interesting. Schwarzschild was in the army on the Eastern Front at that time, in very difficult conditions. And I don't know if you can read here the words from the letter to Einstein. Well, he could find this solution during the battle and all this noise. So it's an example one can do extraordinary things even in extreme situations, if you like. So this is the message for us. And then this was, of course, Schwarzschild solution, vacuum. And it took almost 50 years to find the next great solution, spinning generalization of this black hole by Roy Kerr. So next year we'll celebrate 60 years since the discovery of the Kerr solution. It's again vacuum. This time it's a rotating black hole. It's very beautiful geometry. And then so far, this is what we have most important for the vacuum case. And one may ask how general are these results? Are more general solutions even on the vacuum sector? What about the matter fields? Because so far we equated the right-hand side of the Einstein equations to 0, no matter fields. Yes, the case for Maxwell, this is the case. So if we include a Maxwell field, simplest generalization was being found 1 year later after Schwarzschild. It's the Reisner-Nordstrom black hole, which was rediscovered by a few more people. And there is also a straightforward generalization of Kerr solution, the Kerr-Newman 1, with an extra parameter corresponding to electric charge. Now, so this is the emerging picture for the electrovacuum case. Einstein gravity, vacuum, geometry, plus Einstein gravity, geometry, plus a U1 field, a Maxwell field, electromagnetic field. For Schwarzschild, we have Reisner-Nordstrom, which is again spherical symmetry, a very similar geometry. And for Kerr, we have Kerr-Newman. But we may ask how general is this result? Are there more general solutions? And this is not obviously not so simple answer if you start thinking, because, for example, in electromagnetism, we have all these multipoles. General solution contains an arbitrary number of constants. You start exciting, if you like, dipoles, quadrupoles, and so on for a Maxwell field. And why may I ask, since we have Reisner-Nordstrom with an electric charge, monopole electric charge, do we have also dipole Reisner-Nordstrom type solution or not? And there are some indications this cannot be the case because such solutions exist, but they are singular. So there are some pathologies. And the answer is can be found even more general. There are some theorems. some uniqueness results for Einstein gravity and also for Einstein-Maxwell theories. These are the uniqueness theorems. Again, I'm talking about 4 dimensions, asymptotically flat case. And we have first Israel theorem, which I put here, capture of the paper, first page. It shows that Schwarzschild is unique in the static spherically symmetric, and increasing the complexity, people were able to show a number of famous scientists the uniqueness in the end of the Kerr solution. And also for Kerr-Newman, I think there are still perhaps some loopholes, but basically the result is there. So, for example, we have this Carter-Robinson theorem showing that Kerr is unique among all possible solutions. There are generalizations, but even in the vacuum case, but they possess pathologies. There are some singularities, some problems with analyticity. But let me emphasize, this is valid for 4 dimensions, asymptotically flat case only. If you go, for example, to higher dimension, these results are not valid. Even in vacuum, in 5 dimensions, for example, we have this famous Emparan real black ring solution. And you have with a different topology of the horizon. You have a toroidal. And you have a Kerr-like solution, and at infinity, they may look exactly the same, far away, the same mass and angular momentum, but the geometry, the space-time is completely different. And even in 4 dimensions, if you go to a different asymptotics, to ADS, for example, you have a completely different picture. So 4-dimensional asymptotically flat case is rather special. Again, so this is what we said already. This is the emerging picture. And Carlos mentioned already this famous sentence by Chandrasekhar summarizing the beauty of the Kerr solution. All black holes in the universe, starting from conjectured microscopic black holes to supermassive black holes, all of them are described by just one single solution. It's fantastic if this is the case. So, and so that's why Kerr solution is important. And this simplicity and beauty of Kerr-Newman solution is described by this metaphoric sentence: black holes have no hair. So hair is a metaphor for all complications, all multipoles, all other details. And this expression has been coined by Ruffini and Wheeler in 1971, when these uniqueness theorems started to appear. They were established, and people thought this is the generic case for all possible models, not necessarily vacuum general relativity or Einstein-Maxwell theory. So the general expectation was that a black hole has no hair. It doesn't matter how the black hole has been formed. All physical information is lost. So it can be created. So for example, if I throw this remote control to a black hole, it will only increase with 30 grams or something like that, the mass of the black hole. All other features will be lost. Yeah, so this is a nice picture you so many times, and this is a joke by Hawking in this nice review work. And again, this emphasizes how strong will be such a statement, absence of all possible extra features of a black hole. Everything is described by Kerr or Kerr-Newman in any theory. And this is, again, a joke about the no-hair theorem. Again, it states that a black hole is described by a finite number of parameters like mass, angular momentum, or electric charge, which are associated with some quantities measured at infinity, with some flux of the sphere at infinity. And this is a metaphoric picture again. But let me emphasize, there is no general proof this is valid in any theory. It holds in vacuum, in electrovacuum, and also there are some results if you include a dilaton. but we don't know if this is the case generally. And you need to work case by case to do the study in each case separately. And there are no general proofs. And there are two main directions of challenging this Kerr hypothesis. The first one is to change the theory of gravity, introducing extra fields, extra geometric structures, going beyond the framework of Einstein gravity. And the second one is more appealing, more directly related to our understanding, is to include other matter fields apart from Maxwell. So, or to do them, to consider these two directions together. As we shall see later in the next presentation, the case of some classes of scalarized black holes, for example. And this has been an active area of research over the last few decades, and it's still, there is still some constant progress, I would say. Still some work. Now, what do I mean by including matter fields? I have these slides summarizing the matter content, the Lagrangian of the standard model. These are the fields we know exist in nature, for sure. So we have a spin 0, the Higgs field. We have these vector fields, SU2, U1, SU3, which are gauged for the scalar. The scalar field is gauged with respect to these gauge fields. And then we have the fermions, which are again gauged. And all put together, this gives a non-zero energy momentum tensor. And we shall see the Neuer theorems are violated. They don't hold for the matter content of the standard model, for example. This was not known in the 70s when this Neuer conjecture has been proposed, for example. Okay. Then, what is the meaning of the hair? Let's summarize the situation. So let's start with a generic model. We have Einstein gravity, but it can be more complicated. So if you like, you can include other geometric structures. And then some matter fields, collectively denoted by, psi. And then you have Einstein equations, or gravity equations, take the variation with respect to metric, and matter field equations. Then the study is done case by case, as I mentioned. You have two possibilities: prove a Neuer theorem rigorously, mathematically, and then you stop everything. You are lucky, or not. If not, you try to construct the hairy black hole solutions, if you can disprove the absence of black holes with excited fields psi. So this is somehow how the things work. And I put a few slides with general remarks on this kind of activity. First, there are very few exact solutions. You are very lucky if you find the exact solutions in this area, beyond Kerr, or even beyond Reister-Nordstrom, in fact. We are rather exceptional. They are typically constructed numerically, and sometimes mathematicians came later with existence proofs. It's the case in several cases of main interest. All cases in these lectures are without dynamics inside for the geometry, although the matter fields could possess some harmonic time dependence, if you like, but at the level of the geometry, everything is frozen. We may have only rotation. For spherically symmetric ansatz, typically one takes such an ansatz in terms of two functions and in sigma. In Schwarzschild-like coordinates, this type of metric gauge choice. The advantage is you get directly first-order equations to solve numerically for this function n in sigma. Or if you like, you can relate this function n to mass density, local mass density. So it has some technical advantages for numerics. For the axially symmetric case, we shall see George's lectures tomorrow, no? Yeah. And he will come with more details how to approach this problem. Now, it is always extremely useful to discuss in this no-hair industry to consider the probe limit. That is to study the matter field equations in a fixed geometry. It can be Minkowski space-time or Schwarzschild black hole. Many times it gives a lot of hints about the situation, including back reaction, when solving the full problem. So this is a useful step. Also, it usually, if you have hairy black holes, they are anchored on solitons. So we have to introduce this concept of soliton. For these lectures, we don't ask stability for solitons, or even for these black holes, the question of stability will be secondary. We are mainly interested in their existence. By soliton, we mean something which is topologically trivial. It's a kind of deformation, smooth deformation of flat space-time, Minkowski space-time. Particle-like, it corresponds to our intuition about a particle. No horizon, it's just some curved geometry, asymptotically flatness, and again, no dynamics. Although the solitons started historically as traveling waves, here we don't ask these features for simplicity. And now, there are various cases with solitons in nonlinear field theory in a flat space-time background. They are supported by nonlinear effects. The best known examples are Q-balls with a complex scalar field, monopoles, and sphalerons, and standard model or extensions of the standard model, for example. And in all cases, they survive when including the back reaction. They will curve the geometry. So they survive in Einstein, well, in the theory of gravity. And typically, when you have gravitating solitons, when you have solitons, in fact, in most of the cases, you can put a tiny horizon at the center. That means you have hairy black holes automatically. So this gives a strong indication for if you find the solitons, even without gravity. If a theory has solitons, it means typically you have hairy black holes. Now, a final slide here about the hair. People used to make a distinction between primary hair and the secondary hair. Primary hair means you have a new global charge associated, or a new quantity. The issue of global charge could get quite tricky in this situation, in such a context of hairy black holes, but a new quantity associated with the hair, or secondary hair, which is typically the case. This new quantity is determined by usual quantities which are fluxes at infinity, like mass, electric charge, angular momentum. And finally, let me emphasize again, I think this is an important lesson, it's not safe to extrapolate results from a theory to another, even related theories, and even worse, to higher dimensions or different asymptotics. 4 dimensions is rather special, and asymptotic flat. Let me emphasize again. Now let's do during the lectures, we shall use an approach increasing the level of complexity. So simplest field in nature, technically speaking, conceptually, is the scalar field. Real scalar field. What about black holes with scalar fields? Do they exist or not? And now, why scalar field? First, it's simplest. Many times one uses scalar field as an effective description, as a proxy for more complicated models. And most important, perhaps, we know there is a scalar field in nature, the Higgs field. Standard model, we have a complex doublet of fields with some vacuum expectation value, a specific potential. What about putting together the scalar fields with black holes? And now the case of scalar field is rather special, more difficult than expected. So historically speaking, various solutions with hairy black holes started to be found at the beginning of the 1990s. But not with scalar hair, and that's why this sentence by Mayo and Bekenstein, they couldn't find, there were all kind of no-hair theorems for models with scalar field. And this can be understood by taking the simplest case somehow of a massless scalar field, just usual kinetic term, nothing else. And we have an exact solution found by various authors, first by Fisher, forgotten, and then Jennings, Newman, and Winokur, and then other authors, which is a kind of Kerr black hole with scalar hair, or if you like, perhaps better, scalar counterpart of the Rystrom-Nordstrom black hole, because the scalar field has 1 over RDK at infinity, a kind of monopolar scalar field. You can find, working in the proper gauge, a simple enough exact solution. This is the expression of the scalar field. But it has a naked singularity, and this is a bad geometry. It's not good to do physics with it.
Is it at the horizon, right?
Yeah. You can see here, this is the position of the horizon where GDT goes to 0, and the scalar field will explode. It's log of 0. It goes to minus infinity, stuff like that. So it's sick. But one may ask, what the situation if you go to multipoles? And indeed, again, let's consider this problem into what we said before. You can solve Klein-Gordon equation, massless scalar field in the background of Schwarzschild, and you see automatically all scalar multipoles, in particular here the dipole, would explode at the horizon. You can see here. You can take a scalar usual decomposition of all multipoles in flat space-time. We have this simple decomposition of 2 modes, one exploding at infinity, one at the horizon. In fact, to answer your previous question, you have a solution which is fine at the horizon, but then it will explode at infinity. If you take here C2 equals 0, scalar field will diverge at infinity and will make the space-time non-asymptotically flat. So it will give a distorted black hole at the price of giving up asymptotic flatness. Yes, please always ask if something is unclear or later. Yeah, probe limit, this is what we call. Just give an idea of the generic picture because, yes. But I think there is some work taking into account back reaction. And in fact, this model is exactly integrable. It can be done in Weyl coordinates. You can find generic solutions. But it's less transparent. Okay, so to summarize, there is some tension between black holes and scalar fields. And as you can see, that is not so easy to put scalar fields around black holes. It's rather unexpected. It's different than Maxwell. And there are all kinds of no-hair theorems. But there are also some ways to circumvent these no-hair theorems, as we can see. But let's discuss. So we have to go beyond simple massless scalar field. That's the lesson. And what about Higgs field? We know there is a Higgs field. It exists. It appears in the standard model. It has a Mexican head potential, very special properties. It doesn't go to 0 at infinity. And it has been detected 10 years ago at CERN. It's a quite heavy field for our standard. Well, it's not relevant in astrophysics, I shall see, because it's very heavy. It's called, it gives mass to everything in the universe according to the current understanding via Higgs mechanism when gauging this field. And apart from Higgs, there are all kind of well, Higgs, we know it exists, but there are all kind of indications from various directions about the existence of other scalar fields. And perhaps we'll learn more in Lorenzo's talk, I hope. And there are various extensions of the standard model with all kind of extra ultralight scalars. String theory and extra dimensions implies the existence of all kind of sorts of scalar fields. And in cosmology, inflation, we have the inflaton and so on. Also effective description. And but there is no evidence yet, no experimental evidence for the existence. We have to say that nothing else apart from the Higgs for the moment, just theoretical expectations. Now, how to put together black hole physics with massive scalar fields? There is a simple observation that this is not so simple, because if you take a massive scalar field, then we have a quantum wavelength, as we know from quantum mechanics lectures. And for a Higgs particle, the wavelength is 10 power minus 17 meters. So it's a tiny wavelength. While for a black hole, in particular for black holes in astrophysics, Sagittarius A, at the center of our galaxy, the relevant length scale is Schwarzschild radius, more or less, and it's a huge radius. It's for Sagittarius A is of the order of 2 times the distance Earth to the Sun. So they are very, very different length scales if you take the scales from standard model of particle physics. So the lesson, we have to go to new physics, light and ultralight scalars with a tiny mass and very large wavelengths to put together black holes, I mean astrophysical black holes and scalar fields. And unless we go to microcosm and we are interested in a different class of black holes, microscopic objects, which may have different problems related to quantum mechanics. But for astrophysical black holes, we have to postulate the existence of light scalars. Now, as I mentioned, there are various Neuer theorems. They are summarized in this preprint, this paper which has been published 7 years ago. Various Neuer theorems, various approaches. It's a more technical part, and that's why we summarize here the main assumptions to establish Neuer theorems. There are three assumptions. We accept the scalar field is canonical, I mean usual kinetic term, nothing else, with a standard coupling to Einstein gravity, minimal coupling. Then there is a condition of the scalar field potential, which we assume to be true. And also, the scalar field inherits the space-time symmetries. In particular, we said the space-time is static or stationary with 2 Killing vectors. And the same, we assume it's the case of scalar field. Then there are possible to establish the absence of scalar hair. Well, we don't have time to go into all theorems. We'll just briefly review a classic theorem which is used one way or another by most of our extensions and also for other models of hairy black hole, Neuer theorems, higher spin and so on. So it's a theorem established by Bekenstein, and people used to call this type of theorems Bekenstein argument. It's used many times in various contexts. So you start with, here we don't use the gravity equations. It can be any model of gravity, just scalar Klein-Gordon equation. It is very easy to understand. You start with Klein-Gordon equation. One multiplies this equation with phi. Then next step is to use some identity to replace first term with the total divergence minus kinetic term. It's a standard identity. And then move the kinetic term to the right-hand side of the field equations and integrate over some t equals constant hypersurface, space-like surface. And you integrate from putative from some event horizon to infinity, all overall space outside the black hole. So you use the usual field equation, Klein-Gordon equation, get a slightly changed version of it, modification, get an identity, you integrate it from horizon to infinity. The boundary terms will vanish from regularity if you study the properties of the solutions, presence of a horizon, and finite energy requirements, scalar field vanish at infinity, and you end up with this simple enough identity. which is 0 for massive scalar field or other reasonable potentials, many other reasonable potentials. And since you are integrating a purely positive quantity over some compact region and is 0, it means scalar field should be 0. So that's the spirit of the theorem, quite easy to understand. And then you conclude that there is no scalar here, subject to these assumptions, all these three assumptions we put before. And there are several variations along this line, but there is no time here. Okay, so this is the Bekenstein argument, and people used to say how to understand this no-hair result and why the situation in the electric field is so different. Because there is no flux associated, you cannot define a flux for a scalar field. There is a too simple object. It's a number for each space-time point, if you like. While for a vector, you can define some direction, it is possible to have a flux, some way of doing physics. It's a manifestation of the absence of global charge associated with the scalar field. So it's in the spirit of the expectation based on uniqueness for electrovacuum. So this was one piece of folklore which motivated the community to expect the absence of hair for, generic absence of hair for any theory. But the situation is more complicated. Of course, there are black holes with scalar hair, and there are various loopholes of these arguments. And we shall discuss each case with the corresponding loopholes, for example. First assumption, you get canonical and minimally coupled scalar field to gravity. Well, an early example were the Einstein-Skirm black holes, which were found by Lukoc and Moss. I think Lukoc was a student of Moss in '86, published in a paper in Physics A, but it was ignored by community. It was not taken into account too much. So this is historically the first example of hairy black hole with scalar hair. It's in the Skirm model. The Skirm model started in '61, proposed by Skirm, I think. In '61, if I remember well. It started as an effective theory, flat space, nothing to do with gravity, and it's not the usual Lagrangian of the scalar field. First, you have to consider 4 scalars, but it can be only 3. It's not crucial. Subject to a sigma model constraint, so the sum of the squares is 1 everywhere in space-time. It's assumption, but most important, they don't possess the kinetic term, usual kinetic term only. There is a quartic term, and that's how this no-hair theorem is violated. You get an extra contribution. And so there are black holes with Skirm hair. Here I have some technical slides, but we don't. I think the slides will be accessible to anyone. If there are questions, please ask. And we refer to. Sorry. Standard review with more details on this class of hairy black holes. And related, so again, you have flat space-time skirmions. They will survive in the presence of gravity when they're curving the geometry. And then you can add a tiny black hole at the center. That's the mechanism, what we mentioned already before. A related example are the global monopoles. It's an interesting example, also perhaps more important, because the skirmions are a rather exotic example. They are not part of the mainstream gravitational research, but the global monopoles were important in the 70s. So they are found, they are perhaps important in the early universe. You are working in a model with 3 real scalar fields, and subject to, with a non-zero, approaching a non-zero value at infinity. And with a proper ansatz, people used to call it hedgehog ansatz, it is possible to construct first, again, solutions in flat space-time and then gravitating and put a tiny black hole at the center. So this is a violation of the Nauer conjecture. The problem is, for this case with global monopoles, gauge fields, the mass diverges. So the space-time is, strictly speaking, not asymptotically flat. It will possess an infinite mass. They will be a kind of cosmological defects, a bit like cosmic strings. They are the cousins of cosmic strings, these kind of things. In this case, we have a conical deficit. So it is possible to violate the Nauer conjecture even with normal scalars, like in this model, 3 scalars, Higgs-like, that the mass will be infinite. So it's again a rather exotic example. Now, a different way of violating the Nauer theorems is assumption 2, with a potential which does not obey this condition. And so we need this condition for the Bekenstein argument. This condition is violated. And in this case, you have to postulate some rather curious properties for you, to accept some rather curious properties for your potential. And it is possible even to construct exact solutions, if you like, if you accept this reverse engineering technique. I give here a simple exercise. You choose your own scalar profile. Let's postulate this scalar profile with some power of R. Then you are reconstructing, this is flat space, you are reconstructing the potential which is compatible with this exact solution. That's the idea. And then you can find, for a sextic potential, negative potential, for example, it's a very simple expression in flat space, and it's a finite mass. And it's even more possible to extend this exercise for the presence of gravity. You can find exact solutions with scalar hair. And you can do a lot of exercises because it's exact solution. But at the price of getting unnatural expressions for the scalar potential, which doesn't come from a fundamental theory. It's not a standard model. But it shows as a proof of concept the existence of scalar hair, even in the simplest case of Einstein gravity coupled with a real scalar field, quadratic term, plus a non-standard potential. And there are papers, quite a lot of activity, well, over the last decade, not quite a lot, but there is some activity, in particular this recent paper discussing this one exact solution with 1 over R scalar profile, like Maxwell, electrostatic potential, and you find some more complicated scalar potential and more complicated metric functions, but still with Mathematica you can study all properties. It's more complicated than Einstein notion, but still analytic solution. Fine. What about the Higgs field now? What we have in nature? There are theorems for the Higgs field with gravity, Einstein gravity. There are no black holes. Extensions of the Bekenstein argument in the end. That I'm not an expert here, but there are some smart people, Gregory Moss. They claim Higgs field and gravity can still be put together if you take into account correct quantum corrections to the Higgs potential, which will somehow avoid these theorems via some negative terms. So these quantum corrections will change the Higgs potential. It's still possible to circumvent the Nauer theorems and put together Higgs mechanism, Higgs field alone with gravity. And they found black holes with Higgs hair, but with a distorted Higgs potential. And now, last assumption is on these Nauer theorems was anchored in the scalar field being inheriting the space-time symmetries. And it's again possible to violate these assumptions, to find black holes with scalar hair, and these are the Kerr solutions, and their generalizations were cousins with spin 1. But I'm afraid I run out of my time for today, so we'll continue tomorrow. So thank you very much, and please, I'm waiting for your questions.
Thank you, Eugen, for your very interesting talk. So we can start by if anyone has questions in online, if they want to ask, you have the time now.
Can you hear me?
Yes, you can.
Okay, so hi. First of all, thank you for your very interesting lecture. So maybe I missed something, but could you say a bit more about the second assumption on the no-head theorems? Where this assumption comes from?
Could you repeat the question, please?
So my question is about the second assumption
Yes.
on the no-head theorem.
Yes.
Where does it come from?
Yes. Could you last words, please?
Where the assumption comes from?
It comes from this no-hair theorem of Bekenstein. You see, look at this integral here. First term is the usual kinetic term for the scalar field, which is strictly positive. And then you have a term which is the product between scalar field and the derivative of the potential with respect to the scalar field. If this is positive, then the integrand there is strictly positive, and you get a contradiction. So if you accept, which is the case for a massive scalar field, or for a scalar field with quartic self-interaction, which is also positive, for example, yeah, phi to the 4, lambda phi to the 4, this type of configuration. And then, if you assume that locally these terms, I have a slide, 1 second, yes. So if you accept that the scalar field times the derivative of the potential with respect to the standard field locally is strictly positive, then the integrand is strictly positive, you don't get a contradiction. The only solution is a vanishing scalar field.
Okay. Okay.
So it comes from the Bekenstein type of argument. Okay.
Thank you.
Please.
Okay, so is there any more questions online? Nope. So since there is no more questions online, so here in the room, there is some more. So Pedro, you can ask first.
Yeah, sure. So thank you, Eugen, for this initial part of the short course. Can you perhaps say some words about these solutions with the Higgs hair? I was a little bit intrigued.
Me too. Me too.
Yeah, so it's not really a question. I'm asking you to just expand or elaborate a little bit more on these sort of solutions. Thank you.
So if you keep to the standard Higgs potential, then for the standard Mexican head potential, one can show a no-hair theorem showing that the scalar field should be in the vacuum state, false of true vacuum state. Yeah. No, in fact, it should be the true vacuum state. Yeah. Okay. Oh. Okay. Thank you. Now, these people have assumed that due to all kind of quantum effects, the scalar field, the Higgs potential, gets some quantum corrections, taking into account in kind of effective description of our interactions. This potential, instead of getting the usual, keeping the usual Mexican head shape, gets deformed, and in particular, it can get negative values in some regions of the space. It's no longer positive definite everywhere. If you are happy with this assumption, then mathematically, you can show the existence of hairy black hole solutions, or also numerically, yeah? It is anchored on introducing higher order interactions such that the scalar field doesn't keep the Higgs type, the usual shape, and is no longer strictly positive, and in particular, it violates some assumptions on these derivatives, yeah?
Some comments about specific solutions. So you said
They were interpreted as follow-on, describing the tunneling between two ground states. They may become with some physics. They may be important on the Euclidean section, but they solve also the the field equations on the Lorentzian section.
Okay.
If you remember, Professor Moss gave a talk in 2018 or 17 in Aveiro, if I think. This subject was also mentioned, but working on the Euclidean section of space-time. So these were interpreted as instantons. But again, they solve the field equations also on the Lorentzian section, because time plays no role at this stage.
I see. Oh, thank you.
Carolina.
So next, Carolina.
Hi, Eugen. So you mentioned that you cannot extrapolate these types of hairy black holes for the case of other asymptotics, but you do have clouds for the current antidesiter, I think. So don't you also have hairy black holes for this case?
Yeah, of course, but I meant even some basic results in electrovacuum cannot be extrapolated. Its situation is even here. If you do this exercise of constructing these multipoles in ADS for the electromagnetic field, you have clouds already, electromagnetic dipole clouds in Schwarzschild, and you have exact solutions. So even in electrovacuum case, this this uniqueness theorem don't apply to ADS.
Okay.
So even the simplest stage. And for the scalar field, a lot of things, indeed, you have these clouds, but you don't need a mass term. Some assumptions here, this second assumption, we got a question, is no longer necessary because you are working in a box. That's the physical mechanism. And you can find normalizable scalar clouds in ADS, even in some supergravity models. We can discuss about after
Thank you.
After that, yeah.
Thank you for your lecture, Eugen. Actually, I have a question about this slide. So you said that there was some work about or with back reaction, right?
Here?
About this, yes.
Yeah, yeah. Linné, some authors, yeah.
Does back reaction cure the singularities?
No. Is there. You have exact solutions with multipoles. They are found usually working with this Weil formalism in electrovacuum. But they possess singularities at the horizon, some pathologies always, or at infinity, non-asymptotically flat.
Okay.
No. But they are more difficult to understand because the coordinate system is tricky. You have to work out some problems. Even here, if you look carefully, for the dipole, this is still fine at the horizon. If you take the limit r goes to 2m, this singularity is not there, but is there at the level of f squared. So at the level of the energy density,
Okay.
and if you work at the level of the exact solution of the full problem, it becomes much more complicated. That's why I put this simple exercise to get some physical intuition.
Okay.
And on the top of this, we have theorems showing, proving, subject to some assumptions, the uniqueness of Rice and Nostrum in the work Kerr-Newman. It's a very rigorous proof.
Okay. So I have another question, actually. So you said at some point that the existence of solitons in flat space is a strong indication that hairy black holes exist when you include
Usually
gravity,
this is the
right?
case.
So when they do, I guess that the black holes, the hairy black holes, will always branch off from these solitons. Am I right?
Yes.
Okay. So
Yes.
if you have a theory of gravity in which the solitons are disconnected from the hairy black holes, does this tell you something about the theory in flat space?
Yes, for example, we have this spherically symmetric boson stars. There will be some talks here, yeah? In the spherically symmetric case, you have the solitons, gravitating solitons. These are the boson stars, Carlos mentioned in the previous talk. But you don't have black holes. There are some no-hair theorems, slightly different arguments, not this Bekenstein. So if you have a spherically symmetric boson star, you don't have black hole generalizations, one of the few examples. And then you have also no limit without gravity.
Right, okay.
So but you can still circumvent all these arguments, including rotation, as we know.
Okay.
But anyway, the lesson is, this is rather exceptional. Normally, they'll go step by step. If you have flat space-time solitons, they will survive in the presence of gravity. I'm aware of one counterexample, but we'll discuss after the lectures. There are even, but in 4 dimensions, I think all cases I know they survive. So we have gravitating generalization with Einstein or anything else, yeah? And then normally you can put a tiny black hole at the center. And hairy black hole is a kind of bound state between a Schwarzschild or Kerr black hole with some hairy environment, some other fields around. And then the black hole will start growing and become more and more deformed, going away from Schwarzschild or Kerr and the picture. But that's the generic picture. And to stop here, I think that's the step 0 when starting to study one specific model. Look first for solutions. Try to simplify the picture. No gravity first. And then increase the complexity.
Okay, thank you.
Thank you, Nun. So is there any more questions? No? Oh. One last one.
So about this this way of considering things, so put a small black hole inside of a matter configuration. So if I am at a Newtonian level, this is a simple thing to do, right? Because it's just a superposition of things. So in GR or in any theory of gravity, is there a simple way to extract like what would be the metric, at least, I don't know, considering some hypothesis of this type of configuration? So consider like, yeah, I have initially a boson star and a black hole grows at the center.
Well, I have a number of slides concerning this class of solutions with synchronized hair, with where it is possible to construct a kind of semi-analytical model based exactly on these assumptions. You assume your black hole is Kerr, in this case, at the level of the horizon. So all physics at the level of the horizon, all relations. And then you have some hairy clouds, some hairy environment, this ring of what Pedro George will describe, around, at some distance. And amazingly, it works very well in some regions of the parameter space. So there is some, sometimes you can, this works. We have a paper, we can discuss after that.
Okay, thank you.
Thank you. So let's move on to the next mini course. Let's thank first Dr. Eugen Radu.